Good morning, good afternoon, wherever you are in the world. Thank you for joining the Vibration Sources and EV Systems and E-Machines webinar. Thank you for joining. I'm Rahini Sayal, Romax Marketing Campaign Manager, and our presenter today is Leon Rodriguez, Hybrid Electric Vehicle Drive Systems Engineer at Romax Technology. I'll now hand over to Leon and let him give a full overview of the webinar. Thank you.
Hello, and welcome to my seminar on noise sources in electric drives. The contents of the seminar are, first, I will give a short background on our Romax technology capability in electric drives. I'll describe our unique approach to NVH simulation. I'll then discuss what the sources are of NVH in electric drives. We look at some conventional methods that are typically used to design lower NVH motors. I'll go through how we can calculate motor excitations using finite element simulations, and how we would then evaluate this in RomaxDESIGNER for an example EV driveline. So our eDrives capability stems mainly from our partnership with the University of Sheffield. So we're based in the Electric Machines and Drives group, where Romax has a technology center that are staffed mainly by Romax employees. And here we focus mainly on electric machines and electromechanical capabilities across the different industry sectors for Romax. The group mainly, so we collaborate between Romax headquarters and the technical center at university, so we work quite closely with the headquarters, and we do projects in electric machine design, analysis, and even testing. Our approach makes sure that we achieve all our targets that include NVH, durability, efficiency, and thermal. And we also look at issues such as coupled dynamics, so the interactions between electromechanical, electronic control, and so on. We also support the software development program in Romax, and as part of this, the first software tools for eDriveline, which is the NVH tool, was launched earlier this year. Our partnership with Sheffield also allows us to use the prototyping facilities. So when we work on machine design projects, we can use these facilities to build one-off prototype machines. So for example, we can use the wire routing machine to build lamination stacks, and then the workshop to build housings and so on, and build and assemble machines at the university itself. I've put a couple examples of machines that were built in the university. So the first is a switch reluctance machine that was used for exhaust gas energy recovery system. So it's a very high-speed motor, and it's also meant to work at high temperatures of around 200 degrees. It's for that reason probably that switch reluctance was preferred, because it has that inherent capability. The second machine is to provide a torque boost in automotive applications. So it's an IPM machine that's meant to generate high torque, and this was again built and tested as part of the university. We also have access to various testing facilities. These cover a large spectrum. The two main test cells that are probably relevant to automotive application are, one is the high torque low speed, which can do 2,800 Newton meters at speeds up to 3,500 RPM. So if we're testing integrated units, maybe that's more suited. Similarly, we have a medium torque high-speed rig that can go up 20,000 RPM. So yeah, we can cover a large spectrum of machines using the test facilities available. The Romax approach to NVH simulation, at Romax we find that quite often when motors and gearboxes are designed in isolation, they can work well only in isolation. And when you put them together in an integrated unit, often we find problems that go undetected because of designing these in isolation. By designing both the motor and gearbox to get alongside each other and looking at interactions in the early stages of the design process, we find that we can identify these and then compensate for them in the early stages of design where the cost of this is low. And these interactions again are particularly true for NVH. Just reiterating that if we look at what a typical product development cycle is, as we go down the left side of the we find that that's where all the concept and detailed design work is done and all the decisions are taken that affect NVH. However, quite often we don't do any analysis on that side and we only identify these problems towards the end of the design cycle during the system test. So by using Romax analysis tools, we hope to, or we aim to bring some of this NVH analysis in the early stages of the design that allows us to save a lot of cost and time for trying to correct for these NVH issues if they get identified much later in the product development cycle. So RomaxDESIGNER R17 now has a new electric machine modeler and a vibration analysis tool that interfaces with electromagnetic FE packages. What this allows us to do is model the entire system together and feed in excitations from the motor and the gearbox and see the system response for the entire drivetrain. And this can then the users can then look at the interactions before finalizing any designs, and so capture these beforehand and before building any systems. It also has an automatic machine tool for an electric machine stator, so we can create an electric the state of the electric machine in CAD and mesh this within RomaxDESIGNER. It also has a frequency domain analysis tool that allows you to look at the excitations in the frequency domain and analyze them. Also, we have a post-processing tool that, for example, the image on the right, that allows you to view the results of the dynamic response of the system in a way that you can identify where the problems actually occur. And since Romax does not do electromagnetic analysis in RomaxDESIGNER currently, we have to integrate with third-party FE analysis tools to generate the excitation data for the electric machine. The sources of NVH in electric machines and drives. So for gearboxes, the source of noise is quite simple. They're all related to transmission error. This occurs because gears do not behave as perfect gears. So if you drive your input gear using a fixed speed, the output gear does not always move with the fixed speed, and there's a slight variation, and the frequency of this variation is a function of the tooth passing frequencies. And the forces that these generate on the system can be calculated in RomaxDESIGNER. I won't be going into more detail about gearbox NVH, as this has been done in a previous webinar. On motor NVH sources, we find that these are more varied. They can be split into magnetic, mechanical, aerodynamic, and electronic sources. We'll look at magnetic sources in a bit more detail. These include torque ripple, unbalanced magnetic pull, and radial forces. However, it's not just important to look at the sources, also important to look at the interactions. So for example, we need to see how the radial forces acting on the teeth affect natural frequencies. Similarly, torque ripple can excite a natural frequency. The unbalanced magnetic pull can affect bearing life and noise due to bearings. Similarly, balancing issues within the rotor can affect bearings. Rotor eccentricities can cause unbalanced magnetic pull in the rotor. So these noise sources interact with each other, and looking at the electromechanical interactions of these are key to finding out where the problems lie. So what is torque ripple? Torque ripple is an equal and opposite force on equal and opposite torque that acts between the rotor and stator. So the torque applied for most machines tends not to be smooth, but has a slight variation that occur because of the slotting. The frequency of this excitation is a function of the least common multiple of the rotor and stator poles. So the machine we look at on the right has 8 rotor poles and 48 stator slots. So the least common multiple for those is 48. So the frequency would be 48 times the mechanical frequency. Generally, higher slot pole numbers can increase frequency and reduce issues for torque ripple. Fractional slot machines are interesting because you can use different slot pole combinations to get high least common multiples and therefore lower torque ripple. So for example, the 12 slot 10 pole or the 9 slot 8 pole machine. Although these are good for low torque ripple, they can have high radial forces. So you should take that into consideration when using these kind of machines. What are radial forces? These are forces that act again in the radial direction between the stator and rotor. And although the forces on the rotor tend to cancel out, especially if you're looking at inner rotors, the stator teeth see quite complex force shapes like the one we see on the left. And a way to look at these forces is, even though they look complex in the spatial domain, when we look at them in the frequency domain, we can do a harmonic analysis and break these down into their individual frequency components. And so looking at radial forces in the frequency domain allows us to understand how these shapes are formed using the different harmonic components. Another source of NVH is unbalanced magnetic pull. This seems to be ignored quite a bit in machine design, because machine designers always assume that the rotor sits square within the air gap, but any offset in the air gap can cause a large force between the stator and rotor that acts as a negative stiffness. And this can have a significant effect on bearing life. As you can see, the forces gets split onto your bearings. Also, for higher speed machines, this can cause significant audible noise because they occur at the frequency of rotation. So with people looking at higher speed rotors, this can also cause a large noise issue. What is a typical way of dealing with NVH? The conventional method, for example, in gears is to use tooth contact analysis and calculate transmission error, and then based on that try and reduce the transmission error. The Romax method looks at it in a slightly different way, in which we look at the response to the transmission error and then concentrate on reducing the response rather than just the transmission error itself. And this method applies to electric machines as well, where one can calculate torque ripple and radial forces using electromagnetic stimulation and then try and reduce those. But if we look at the response to these forces that we see in the system and concentrate just on reducing the response, we can often find better solutions to the NVH problem. So what's conventionally done in terms of reducing NVH in motor design? Right from the beginning, I think selecting a motor topology has quite a consequence on the NVH. There are several different topologies available. For example, the surface mount PM or the interior PM or the switch reluctance or the induction machine. They all have different advantages and disadvantages, which is why picking one for any application can be quite tricky. And we see this especially in automotive, where a lot of different vehicle manufacturers have gone for different types of electric machines. So one should consider NVH right from the beginning when selecting motor topologies. Other techniques include increasing number of phases, changing slot pole numbers, skewing the rotor or stator, modifying reluctance of the motor geometry. We can look at changing control method to cancel out some of these noise sources. And in extreme cases, you can also reduce the air gap flux density to reduce the noise source. All these tend to reduce performance, increase cost, and if one doesn't know what the response is, they might not really affect your NVH because the response might not be affected by the solution you choose. Motor skew looks something like this. If compared to gears, it's moving from a spur gear to a helical gear, so you have in this case, on the right, the rotor teeth skewed to average out rotor torque. This is particularly effective in reducing torque ripple, but it does reduce the average torque as well. And it can also increase manufacturing complexity. It's quite commonly used in induction machines. However, in PM machines, especially the rotor, it's a bit more trickier to manufacture with skew, so it's less used. Geometry modifications, such as including slits and notches to modify the reluctance, or increasing the number of rotor slots in synchronous reluctance type machines, are again methods to reduce torque ripple and excitation. And in PM machines, one can also use sinusoidal PM shaping. So this is a method to make your air gap field more sinusoidal and reduce the harmonic content of your field, and therefore minimize excitation. So how can we calculate motor excitations using finite element simulations? Before we calculate anything first, we should see what we need to calculate. In RomaxDESIGNER, at each level of load, we would need a set of simulations done at different speeds, and for each simulation, we would need to calculate the torque ripple versus rotor position, and the stator force or radial force acting on each tooth for one mechanical period. So this data can be calculated in third-party finite element analysis softwares, and can be output as a time series in a generic CSV format. In RomaxDESIGNER, we can then import this file, import this data, and do a harmonic analysis using the preprocessor, and then feed it to the dynamic analysis module to calculate the response to this excitation. This is just a a selection of the many finite element softwares available for electromagnetics. And yeah, these are all capable of calculating the excitations, but I will show you how we do it in ANSYS Maxwell in the next slides. And we'll do this for an example EV driveline. So this is what the example file looks like. It has a 50 kilowatt IPM motor that goes up to a peak speed of 12,000 RPM and has an overall gear ratio of 12:1. So the gear stage is a two-stage gearbox, and it also has an integrated motor drive that sits along with the unit. The motor, in a bit more detail, is a 48-slot 8-pole IPM motor that produces a peak torque of 210 Newton meters and is driven using a 300 volt to 50 amp drive. This is what it looks like in geometry, a typical IPM motor. And then when you solve a simulation of this sort in ANSYS, you can use a 2D solution, and you would solve this as any other machine in the software package. The only change one needs to make to calculate the excitations is to define two sections as separate entities and calculate excitations for those. And this is how you would do it in Maxwell. So what I've done is just separated out the teeth as separate objects and assigned a force to them. I've also segmented this machine into 8 sections, so it's much faster to solve. And if you assign the force component, then it will calculate the radial forces. We then need to define the phase current excitations for a given torque speed condition and analyze this. To get it over a set of torque and speed ranges, you can run a parametric analysis for the different conditions. Also, if you want to include the effect of control, you can run your simulation along with a circuit coupled simulation that includes the control parameters within them. Once you run the simulation for each condition, you would need to get a data table of the time series for the torque, and again something similar for a time series for the tooth force excitations for each tooth. And when you do have those, you can extract those into a CSV file quite straightforward in this package. Once you have all the two excitation data, you can open the preprocessor in RomaxDESIGNER, and that allows you to enter the radial forces and the torque ripple. So you can just add a speed condition and open the CSV file and copy and paste these. A bit more detail on how we do this is available in a webinar delivered by Christian a few weeks ago. So once we enter all this data into RomaxDESIGNER, we can do a bit of processing to look at what the harmonics are. So if we calculate the radial harmonics, you can see that on the right, you can see what the dominant harmonics are and what their magnitudes are. And that gives you an idea of what your excitation looks like. When you run the simulation in RomaxDESIGNER, it produces, you can produce a result showing the mean square velocity responds to different excitations that you've applied. So the first looks at the response of the 48th harmonic from the electric machine, and you can see it's causing a vibration on the gearbox and the power electronics. That same harmonic again causes vibration in on the fins at around 8,000 RPM. Using the same tool, we can also see the deflections caused by the transmission error in the gearboxes and an unbalanced force on the rotor, for instance. So this tool allows you to look at the response to all the different sources of excitation side by side, which is quite handy. So let's look at the vibrations caused by the electric machine in a bit more detail. So we saw that the 48th harmonic was causing vibrations at first at around 1,000 RPM. If we go back to the pre-processing tool and look at the frequency domain harmonics at 1,000 RPM, we find that the 48th harmonic is actually quite small and has been ignored at this speed. So it's definitely not the radial forces on the stator causing this. However, if we look at the torque ripple, the 48th harmonic is the dominant harmonic. This is because the LCM, as we looked earlier, for the stator and rotor is 48, being a 48 slot 8-pole machine. If we go to the higher speed, so if you look at the 8,000 RPM condition, and we look at the stator teeth, the 48th harmonic has now become dominant, and the reason for this is at 8,000 RPM the machine is now in the field weakening region, and that increases the excitation for the 48th harmonic, causing this issue. So it's interesting to see that even though you have the same harmonic for the motor causing the issue at two different speeds, they're actually because of two completely different forms of excitation. So yeah. Okay, to summarize, we looked at the sources of NVH in e-drives and what the typical methods are for mitigating NVH in machines. We also looked at what the methods are to simulate the effect of NVH sources both from motors and gearbox, and how we would do this in Romax. What a typical method is to generate excitation from a third-party finite elements, electromagnetic finite element software. And in general, a system approach is required for achieving good NVH results, because an excitation from the motor can cause a vibration in the gearbox and vice versa. So it's important to see the response of the entire system rather than just the motor and gearbox in isolation.
Thank you very much, Leon, for presenting a great webinar. Now, as we've now started our Q&A session, please type in your questions in your GoToWebinar toolbox.
Okay, so thank you for your questions. I've got a few questions here. I'll try to answer them one by one. One question is, can I explain what the harmonics and the radial forces are from? So yes, these come from a number of different sources, but the main source for the harmonics are the slots in the stator. If you look at the stator, the windings, they won't have a continuous sinusoidal shape, and these slotting usually introduce harmonics because they have very discrete states between them. So that's the main source for the harmonic. If you take off the core in the stator and have just an air stator, which have been done in some machines, you can get rid of forces or the harmonic forces. You'll still have the forces from the fundamentals. Another question saying, can I use analysis from EM and ANSYS mechanical to perform further gearbox analysis in Romax? So I'm actually if you can get back to me with that in a bit more detail, I might be able to answer that. I'm not sure what you mean by what data from an ANSYS mechanical you're looking for. But as I showed you regarding electromagnetic analysis, you can solve it in ANSYS and then export it into CSV and then import it back into Romax. So apart from torque ripple and radial forces, what are the other unique issues that can be expected in EV in comparison to ICE vehicles? Yes, so in general, designing gearboxes for EV vehicles are relatively different. Quite often they use single-speed gearboxes that have quite high gear ratios. So whereas an ICE engine would run at a few thousand RPM, you can have e-machines running at 12,000 and 15,000 RPM. So you have a lot of high-speed effects that come into play. Also, if you use multi-speed gearboxes, you have shifting between gears, and these shifts tend to be between larger ratios in e-machines as opposed to ICEs, where you can shift between smaller speed ratios. So the quality of your shift and so on becomes an issue, and the NVH issues during your transients might become more problem. One more question. Can it analyze the dynamics of the gear and motor system when running? It is analyzing the dynamics for the entire system across different speeds. So that is effectively under load conditions when running. And I think that's all we have time for. Again, thank you for joining the webinar and for sending the questions. I'll hand over to Rohini.
Thank you very much, everyone, for sending your questions through. And as Leon said, that he will answer any remaining questions by email, which he didn't have a chance to answer today. So, yeah, if you do feel you would like to ask a question but didn't get a chance to put it through to us on this webinar topic, or if you would like to contact Romax representative on our electrification team, please email marketing@romaxtech.com and we'll get back to you as soon as possible. Please visit the webinar section on our website for upcoming webinars. We have the Simulating Lateral Vibrations in High-Speed Motor Shaft webinar presented by Barry James, Chief Technical Officer and Head of R&D at Romax Technology, on Thursday 17th of November at 8 AM and 4 PM GMT time. We hope you'll be joining one of our future sessions. Thank you and goodbye.